Hello dear students, this is your Engineering Mathematics 3 lecture. Today's topic is simultaneous linear differential equations and applications. Simultaneous linear differential equation. This topic is from unit 1, linear differential equations with constant coefficients. Simultaneous differential equations means simultaneously you solve the system of linear differential equations, like the system of linear equations. We solve the system of linear equations like that. You solve the system of linear differential equations. See, the differential equation in which there is one independent variable and two or more dependent variables. For example, dx by dt plus y is equal to t, and second differential equation dy by dt minus x is equal to e raised to t. In this example, x and y are two dependent variables and t is independent variable. So in RHS there is function of t because t is independent and x and y are dependent variables here. So here t is independent variable and x and y are dependent variables. Such a type of equations or system of differential equations are known as simultaneous differential equations. Now we want the solution for the system of linear differential equations. Now how to solve? See the example. Solve du by dx plus v is equal to sin x and dv by dx plus u is equal to cos x. These two different linear differential equations are given. We solve simultaneously given that when x is equal to 0, u is 1, v is 0. These initial conditions are given. Using initial conditions, we can remove the arbitrary constants. After finding the solution, general solution for this simultaneous differential equations, we will think or we will discuss about these initial conditions. Now, how to solve these simultaneous differential equations? You put here d by dx is equal to d, so that your equation 1 reduces to du, because d by dx is d, capital D. So du plus v is equal to sin x. And second equation, d by dx is again capital D. So this d by dx is d into v. dv plus u is equal to cos x. So that equation reduces to like this. Now you remove either variable. Here in this simultaneous differential equations, u and v are dependent variables. They depend on the variable x. X is independent. That's why in RHS there is function of x for both the differential equations, sin x, cos x, because x is independent. U and v are dependent variables here. So now this is the reduced form of that both the equations. Now you remove either u or v, and you will get the equation in terms of u and x, or v and x. Either remove u or either remove v. Now we are going to replace here v. Now to remove v, you multiply first equation by d and second equation by 1. So that equation reduces to first equation multiplied by d into d square u plus d into v is equal to d sin x. See this equation. Second equation multiplied by 1. So it will be as it is. U plus dv is equal to cos x. Now we are going to remove this v here. So subtract these two equations. Give minus sign. So give negative sign to every second term. So d square u minus u, dv minus dv get cancelled is equal to d of sin x. You know d means d by dx, derivative of sin x. Derivative of sin x is cos x. Cos x minus cos x 0. So RHS term is also 0. Now u is common, so the equation is d square minus 1 into u is equal to 0. This is the LDE. This is nothing but LDE. After solving the simultaneous differential equation, we reduce it to LDE. This is in the form of phi of d into u is equal to f of x is here 0, your function is 0, then in that case no need to find its pi, because pi depends on the function f of x. If f of x is 0, function is 0, then its pi is obviously 0. So state here auxiliary equation. Auxiliary equation is here d square minus 1 is equal to 0, and the factors for d square minus 1 is equal to 0 is they are 1 and minus 1. So complementary function is here c1 e raised to x plus c2 e raised to minus x. Now this is complementary function, and pi, its pi is 0 because function is 0. So its general solution contains only complementary function. U is equal to, where we have the value of u because this equation is in terms of u and x. D square minus 1 into u is equal to 0. So the value of u is here complementary function only, c1 e raised to x plus c2 e raised to minus x. Now this is the value of u. Now you find out the value of v. How to find v? You just differentiate this u with respect to x. You will get the derivative du by dx. Why we are differentiating? Because we want the value of v. We are solving the system of simultaneous differential equations, means our aim is to find the values of dependent variables. Here dependent variables are u and v. So our aim is to find the values of u and v. And the values of u and v will be in terms of x, because x is independent variable here. Now we have the value of u, and we are differentiating u with respect to x, because if we have the value of du by dx, then after putting in equation 1 the value of du by dx, you shift this term of du by dx in RHS, so that you will get the value of v. That's why we are finding du by dx. So the value of du by dx is here. Du by dx is after finding u, you differentiate u with respect to x. So it is c1 e raised to x derivative is e raised to x. C2 as it is, e raised to minus x derivative is e raised to minus x into minus 1. That's why minus sign is here. Now put the value of this derivative in equation 1. So you will get c1 e raised to x minus c2 e raised to minus x plus v is equal to sin x. And so v is equal to, we shift remaining terms in RHS. So it is sin x minus c1 e raised to x plus c2 e raised to minus x. Okay. Now these are the values of u and v. Now the special or initial conditions are given, that when x is equal to 0, u is equal to c. The conditions are given here. When x is equal to 0, u is 1 and v is 0. So put x is equal to 0 in equation number 3. When x is 0, e raised to 0 is 1, e raised to 0 is 1. So c1 plus c2. So x is equal to 0, u is equal to 1, and v is equal to 0. So u is equal to c1 plus c2 when x is equal to 0, and the value of u is also 1. So in next see, this u is equal to c1 plus c2 is nothing but 1 is equal to c1 plus c2, because the value of u is also 1 when x is 0. It is given. And in for v, when x is 0, v is also 0. When x is 0, sin 0, 0 minus c1 e raised to 0 is 1, c2 e raised to 0 is 1. So it is minus c1 plus c2. Equation number 4. In equation 4, you put x is equal to 0. So this term is nothing but minus c1 plus c2 is equal to, what is v? When x is 0, v is also 0. So this term is minus c1 plus c2 is equal to 0. So we have these two linear equations. When we solve these linear equations, solve means you just add these two equations. If we add these two equations, where 2c2 is equal to 1, means c1 is equal to 1 by 2 and c2 is equal to 1 by 2. So after getting the values of c1 and c2, you put in equation 3 and 4 the values of c1 and c2. So we have u is equal to e raised to x plus e raised to minus x by 2, and v is equal to sin x minus e raised to x minus e raised to minus x by 2. These special conditions are given, so we can remove the arbitrary constants c1 and c2. These special conditions are given in this particular example. If not given, you just find the values of dependent variables. You stop there. That is your aim only. Here the special condition is given that when x is equal to 0, u is 1 and v is 0. That's why we are doing all these steps after finding u and v. We are removing the arbitrary constants c1 and c2 from the equations because special conditions are given. If these special conditions are given, then and then you do the remaining steps after finding u and v. Okay, this is one example. Try to solve this second example. Solve dx by dt plus y is equal to e raised to t. Second equation minus dy by dt plus x is equal to e raised to minus t. In this equation, x and y are dependent variables and t is the independent variable. So your aim while solving this simultaneous differential equations is you find the values of x and y in terms of t, like the first example. In first example, u and v were the dependent variables and x was the independent variable. So we have the values of u and v in terms of x there. So like that you solve this second simultaneous differential equation. Try yourself. Now next topic is symmetrical form of simultaneous differential equations. Now what is symmetrical form of simultaneous differential equation? The general form of symmetrical simultaneous differential equation, symmetrical form is dx upon p is equal to dy upon q is equal to dz upon r. This is the form, then it is called symmetrical form, where p, q, r are functions of x, y, z and said to be symmetrical simultaneous differential equations. The solution of such a system of equations is given by a pair of relations u of x, y, z is equal to c1 and u of x, y, z is equal to c2, which are independent of each other. Means when we solve symmetrical simultaneous differential equation, then we have two sets of solutions, u of x, y, z is equal to c1 and v of x, y, z is equal to c2, which are independent to each other. Remember it. Now there are two methods to solve the symmetrical simultaneous differential equations. First method is method of combinations or grouping. Now in this method, we select two groups such that the third variable gets eliminated. That is, we get the variable separable form. Then integration of this gives one part of the solution. Similarly, find second solution which is independent of first solution. Understood? In this method, we select two groups such that the third variable gets eliminated, and that is, we get the variable separable form. After variable separable form, you can integrate it. You know that. You see the example. In the first example, solve dx by dy, dx upon xy is equal to dy upon x square is equal to dz upon xyz. This example is given. So it is clear that we can easily identify that it is symmetrical simultaneous differential equation because it is in that form, dx upon p is equal to dy upon q is equal to dz upon r, where p, q, r are the functions of x, y, z. So you consider either first two ratios or second two ratios, so that we can separate. We have to choose the two ratios such that the third variable gets eliminated. Suppose here we choose first two ratios, dx upon xy is equal to dy upon x square. So in these two ratios, this x get eliminated, x get cancelled. So the simplified form is dx upon y is equal to dy upon x. Here the x square term is there, so one x get cancelled. So the remaining one x is here. So the term is dy upon x. Now you just do the cross multiplication. You do the cross multiplication. It is x dx is equal to y dy. Now this is variable separable form because the terms of x are collected in LHS and the terms of y are collected in RHS. Now variable separable form, so integrating we get integration x dx is equal to integration y dy plus c constant of integration. Now integration of x is x square by 2 is equal to integration of y is y square by 2 plus c, and so it is x square by 2 minus y square by 2 is equal to c. So if we multiply every term by 2, then the term will be x square minus y square is equal to 2c. 2c is again a new constant called c1. So the solution is x square minus y square is equal to c1. This is one set of solution that we have mentioned. We have to find out two sets of solutions. That for one of them is x square minus y square is equal to C1. Now, how to find the second set of solution? You consider the second and third ratio, or first and third ratio. You choose so that we can easily eliminate the third variable. Now, if we choose first and third ratio, dx upon xy is equal to dz upon xyz, then easily we can remove x. We can cut the variable x and y here, so that we have the terms dx is equal to dz upon z. So here the variable separable form is here, that all the terms of x are in LHS and all the terms of y are, sorry, all the terms of z are in RHS. So it is a variable separable form. So integration dx is equal to integration dz upon z plus c. So integration of dx is x is equal to integration of 1 by z is log of z plus c. And so the solution is x minus log of z is equal to c2. So this is the second set of solution. So first set of solution is here, x square minus y square is equal to c1, which is independent to this second set of solution. X minus log z is equal to c2. Okay, so this is one example. Now second example, solve dx by 2x is equal to dy upon minus y is equal to dz upon 4xy square minus z. Now here you consider first two ratios, dx upon 2x is equal to dy upon minus y. So variable separable form, you just integrate it, no need to simplify. It is already a variable separable form because all the terms of x are in LHS and all the terms of y are in RHS. So integrating we get 1 by 2 constant. Integration of 1 by x is log of x is equal to integration of 1 by y is log of y. Because of minus sign, we can shift the term in LHS, so that plus log of y is equal to log of c1. Constant of integration is log of c1 here, because in LHS both the terms are log functions, so you consider the constant of integration, so log of c1. So it is 1 by 2 log of x. So if we shift this 1 by 2 as a power of x, then we will get root x log of root x plus log of y. Log a plus log b is log of a into b, so log of root x into y is equal to log of c1. Log functions are equal, so the term values are equal, so y into root x is equal to c1. If we squaring, we have xy square is equal to c1 square. Xy square is equal to c or c1 dash, you will get again a new constant. C1 square is again a new constant. C2, sorry, C1 dash or something. So after squaring, you just suppose this is C1 dash, then you will get new constant C1 here. Suppose the previous one is C1 dash, so you will get here C1 here. If it is C1 previous one, then you give new name to the new constant C1 dash here. Okay, so xy square, because it is arbitrary constant, so you can write any letter here, but it is a constant term, you remember it. So xy square is c1. So also now this is one set of solution, xy square is equal to c1. Now we want the second set of solution. So for second set, you consider the first and third term. So first ratio is dx upon 2x is equal to, third ratio is dz upon 4xy square minus z. Now in second ratio, the third ratio dz upon 4xy square minus z, we cannot separate the terms because in denominator there is a subtraction, and that we don't want that variable y there, because first ratio is of x and second ratio is here of z. So we want to eliminate here the variable y, but we cannot eliminate it easily. So better way, there is the first set solution is xy square is equal to c1. So you replace this xy square by c1. You replace it by c1, xy square by c1, then your term will be dx upon 2x is equal to dz upon 4c1 minus z. 4c1 minus z. Now here variables are separated. All the terms of x are in LHS and all the terms of z are in RHS. So variable separable form, so you just integrate it. Integrating that 1 by 2 constant. What is the integration of 1 by x? It is log of x is equal to RHS term, you just integrate. The integration of 1 upon 4c1 minus z is log of 4c1 minus z upon minus 1, because the variable is z and the coefficient of z is minus 1. So write in denominator minus 1, plus all the terms are in log function. So you consider the arbitrary constant log of c1, sorry, log of c2. So 1 by 2 log x is equal to minus log of 4c1 minus z plus log of c2. So it is log of root x. 1 by 2 you write as a power of x. So x raised to 1 by 2 means root x. Log of root x plus log of 4c1 minus z means log of a plus log of b is log of a into b. So log of root x into 4c1 minus z is equal to log of c2. So log functions are equal, so values are equal. So 4c1 minus z into root x is equal to c2. And so root x into 4, you replace the value of c1 here. In second set of solution, it is xy square. So root x into 4xy square minus z is equal to c2. So this is the second set of solution. And so this is your answer. So we have two sets of solutions. This one is first, and so this is second set of solution, and first set of solution is here xy square is equal to c1. And so here that first method, grouping method of symmetrical simultaneous differentially simultaneous symmetrical simultaneous differential equation is over. These are two examples. So you take it as a homework. Try to solve these two examples. And here that first method of symmetrical simultaneous differential equation is over. Thank you.